She's now a research director at CNRS in Paris. And she's a world expert in infant speech processing. And she's going to talk about baby steps to language.
Thank you. Actually, I'll get started with something very simple, just asking you a few questions. And this is not a test. No one's going to get more points if you get them right. It's just to get you warmed up to the idea of looking at this very special kind of intelligence that was broached by Jan in the previous talk. So, which of the following statements are true? Please raise your hand if you think it's true that when you're born, when you're just, say, 0 days old or 2 days old, you already show a preference for your native language. Okay, few people think that's true. Please raise your hand if you think that's false. You're all wrong, all of you. The people who said it was true are right. So it's quite interesting. That means that even before we're born, we're already picking up on some things. We're already becoming specialized to the environment we're going to live in by listening in from our mother's belly. Okay, so next one. Please raise your hand if you think that newborns know their own name. Okay? Raise your hand if you think that's false. You're right. Actually, they don't know their name. Okay. How about by 6 months? By 6 months, do they know their name? Raise your hand if you think it's true. Raise your hand if you think it's false. You guys are wrong. They actually do know their own name. Okay. How about saying their first words? Can 6-month-olds say already meaningful words? Raise your hand if you think it's true. Now raise your hand if you think it's false. Indeed, at 6 months, very few babies say their first words. On average, it's actually at 12 months. On average, some kids are doing this earlier. 6 months is really, really early. Some people do say they do, but usually it's their parents, and who knows if that's true. Okay, so nonetheless, many things are happening in that first year of life. And clearly, we know that these processes are the function of several different components. So let me give you a way of representing this process in a very broad way. So what does it mean to learn a language? We can imagine that there's 4 key components. The first one is some kind of mental representation or brain representations that are appropriate to the native language we're listening to. As the child grows older, so these we know exist already when they're newborns. As they grow older, by the time they're 1 year of age, these are already emerging because someone is providing input for the child, and the child is applying some kind of learning function or algorithm to that input. And again, we know that that happens even before they're born, so there's something that's coming inside their brains that's allowing them to do this. And when they're old enough, they might start producing some output, they might start producing some words that people around them understand, and to the extent that people around them believe this is useful, they might change the way they talk to the child. So this is kind of a complex system because that means that the mental representations they have might be reflected in the way that the child talks, and that might actually impact the way people talk around them. And so to model the whole thing together, we would have to model basically the world. That said, we can start with these 4 key components. And this is just a very broad way of representing it. Now, this is one way of approaching this question, but let's now dig into a little bit deeper how they can figure this out. And so again, I'm going to ask you to guess on the following. The same as before, we'll guess which ones of these are true and which ones are false. Humans and chimpanzees share a majority of their genetic information. Who thinks that statement is true? Who thinks that statement is false? Excellent. Oops. Sorry. Well, it's actually true. Okay. In terms of their visual skills, so this one it has a complex linguistic structure. Sorry about that. in terms of their visual skills, humans and chimpanzees are more similar to each other than, say, humans and killer whales are. Killer whales, do you guys know what killer whales are? Orcas, kind of similar to dolphins. Okay, raise your hand if you think that's true. Raise your hand if you think it's false. You guys are wrong. Actually, we are more similar to chimpanzees than we are to whales in terms of our visual skills. Some of the reasons might be that killer whales are adapted to a marine environment, so they need other things. Like us, they're hunters, they're group hunters, so some things might be similar, but nonetheless, it's still the case that our vision is more similar to that of chimpanzees. How about for language? In terms of communication systems, are chimpanzees and humans more similar to each other than humans and killer whales? Raise your hand if you think that's true. Okay, raise your hand if you think that's false. I don't see enough hands. People are really uncertain. You don't want, as I said, no grades are coming across this. Okay, the answer is it's actually false. Humans and killer whales have a communication system that is extremely complex. Chimpanzees do not. You raise a chimpanzee in isolation. You take it out of their group. You look at two different groups of chimpanzees, and basically their communication system is identical. This is not something that they learn. This is something that they just have completely innate. Whereas, for instance, for us, as for killer whales, we are social learners. We pick up on the language that we hear, and we have different dialects, and we have different languages. So these are things that makes us more similar. Nonetheless, in the 70s, we didn't really know this. And so many people asked the last question: can you raise a chimpanzee to speak or to sign human language the way that humans do? I won't tell you the answer to that one straight away. I will tell you about this famous experiment. In this famous experiment that was published in Science before all of you were born, and me too, fortunately. In this famous experiment, they looked at 3 small individuals. 2 of them were human. 1 of them was a famous chimp called Nim Chimpsky. There's actually a movie about him, so you can look him up. What they looked at is their language development, and they thought at that time that language development started when people started producing. And so they started looking at a rather late age. You see here it's about 3 years of age. So one of these children was your typical child. She was learning spoken language, language like English or like French. And what you see plotted here on the x-axis is her age, starting at about 3 years of age. And on the y-axis, you see the average number of words per sentence that she produced. What should be obvious to you is that she starts saying basically 1 word per sentence. And as she grows older, her speech becomes a lot more complex, and she starts putting words together. So this is something that you might have observed yourself. Another data point came from Sarah. Sarah was actually learning a sign language. She was not learning a spoken language, but her parents actually used this sign language and were comfortable with it. In case you guys don't know, sign languages can become fully fledged languages. They have all the complexity that spoken language do. But the difference is that you, instead of using your voice, you actually use your hands. I'm going to need to drop the microphone to show you. So this, for example, is going to be the word apple. This is the word for dad. And I can also say something like, dad gave apple to child, or something like that. So you can put words together in sentences, or put signs together in sentences. So what you should see here is that Sarah also showed this incredible expansion in terms of complexity of her production. You should also see that she was doing this much earlier than Ruth was. And that's a general finding, that sign languages are actually learned faster than spoken languages. Now, people knew in the 70s that chimpanzees couldn't produce language. They thought this had to do with the fact that their communication system is innate, and so you cannot really get them to modulate their mouth the way that we can do it. So what they thought is, we'll teach them sign language. They can definitely move their hands. We can shape their hands for them. We can really show them. And so these are the results for NIM. NIM actually was unable to string signs together, unlike the two humans, and actually unlike any other human that you will find, including some that might have quite severe cognitive issues. So this clearly shows that, once again, we're born with this amazing capacity to learn. This is certainly written in our genes, but it's written in a very small part of our genes, the part that we don't share with chimpanzees, in a way. Another evidence that highlights both the role of the innate capacities and the role of environment comes from a study that came out last year in Cognition, which is a beautiful study that's based on 2 billion people. So in this very simple study, people were asked very simple grammatical questions. You know, do you say in English, do you say I walk to school, or do you say I to school walk? Very simple questions, some of them more complex than that. And after getting these responses from about 2 billion people, they drew curves like this one. Each curve actually is fitted to the data of one group. The red top curve corresponds to monolinguals, people who had only been exposed to English their entire life. The orange curves actually shows curves that are fitted to people who were exposed to English at later ages. So you can see the numbers up here indicate the years at which they were exposed. So between 0 and 9 years of age. And the further down you go, the later you were exposed to English. So the way to read this graph is that regardless of your current age, if you were exposed to English relatively late, then your chances of scoring well on this task are lower. Another way of explaining this is that there's a critical period or a sensitive period for language acquisition. You need to get your input for it, right? Because in fact, as people grow older, they become better on average. But you also need to get it really early. Okay. So that's kind of interesting in this old model that we had been thinking about in terms of what are the key components of language acquisition. Often we forget about this, but these are the ones that I believe are most informative for people who are interested in artificial intelligence. Because this is something that you cannot get from the environment in a way. This is something that you bring to the task, that the artificial or the human agent or the natural agent brings to the task. Okay, so let's go back to this scene where someone, the little child, is acquiring the language that the adult is providing. What of these, how does this work? How do these components interact with each other? It turns out that we do know a lot about how that happens. Based on studies like the ones I mentioned, do newborns recognize their native language? Do 6-month-olds recognize their name? There's a lot of literature on this. But when you start looking at those data, you realize that actually most of it comes either from North America or from Europe. Whereas if you look at the population of children in the world, most children are growing up in Asia and Africa. They're certainly not growing up in Europe. As you know, your population is actually aging right now. And some of you might think, well, does it really matter? But you guys should know, everyone's talking about bias, right? Bias in any kind of artificial agent who's trained with data. We have the same problem with theories. Our theories are based on data that are biased. Still, I'd like to know, please raise your hand, if you grew up in Europe. Big majority. Not unexpected given that we are in Europe right now. Can you raise your hand if you grew up in North America? Just one, okay. I didn't expect that. I thought there would be more. Raise your hand if you grew up in South America like me. Yeah. Okay. Anyone here grew up in Africa? Okay, great. And how about Asia? Wonderful. Anyone from Oceania? Really? Well, welcome. You're far away from home. Okay, so I'd be really curious at question period to hear about some of the things I'm going to say now about why it's not really continent, but why lifestyle associated to different geographical distributions matters. I would love to hear from you guys what you think about this. So why would it matter? When we think about the average child whose language is being studied, they will be growing up in North America and Europe. And the situation in language acquisition kind of looks like this. There is a lot of input. The input is really important. In fact, there's entire books dedicated to explaining to parents that adults are the best source of language for children, because we can figure out how to say things correctly. We have a stable linguistic system. We've learned how to talk. And also, we have a very developed theory of mind. We can understand other people's mental states. In fact, sometimes we even believe that we understand our own child's mental state. I don't know if that's true, because I've been studying babies scientifically for 15 years, and I'm pretty sure I have no idea what it's in their heads. But adults who have children themselves, parents believe they do. And so that means that they can do things like adapt to the child, follow the child's attention, see what they're looking at and talking about that. You know, you can do many things. And you can also use this thing that's called parentese, which I've become an expert on, because I can talk like this. And then it sounds very cute for babies, and they pay more attention to you. So this kind of advice isn't just there for parents who are motivated to read about it. It's actually being produced and distributed in massive interventions all over the world. Perhaps the most famous example came from the 30 Million Words Initiative, based on this idea that in the US, kids from lower socioeconomic status households hear 15 million words by the time they're 4, whereas kids from higher socioeconomic status households hear 45 million words. Okay, so there's a 30 million word gap, they say. The kids from a more advantaged household hear this many words more, and that's why they're doing better in school and they have better language skills. But after that, it actually took over the world. So here's a few more examples of different programs, some of them in the US. And the one that I wanted to highlight, maybe because I'm South American, I think telenovelas are fun, is this one, which is actually a TV show about some families, which in addition to the usual telenovela thing of, you know, the evil twin and the brother who is with a stepmother or something, you also teach parents how to raise their children. In particular, you tell them to talk to the child a lot and to follow the child's attention. So input is really, really important today in theory and in practice. And I think that maybe has to do with this average family that's being studied. In the kinds of settings where we are, that means that we live in industrialized settings. We typically live in cities. We tend to have higher socioeconomic status. We tend to have higher levels of education. Families tend to be smaller. There's fewer children. And typically, and it's even sometimes recommended, that there will be a single figure, a single adult who's taking care of the child. And this is very, very different from the way that many other communities raise their children. Very often, they will be in rural settings. They will have lower socioeconomic status and lower levels of formal education. They might actually not go to school at all. They will tend to have more children, and actually they will share caregiving with other adults and sometimes even with older brothers and sisters of the child. And based on not these findings, but the general idea that in psychology we have this biased view of the literature, Heinrich and their peers coined this term of weird, meaning strange, but also meaning these data come from Western, educated, industrialized, rich, and democratic countries, and it might not generalize to other settings. In fact, it might not generalize to humans at all when we speak generally. So what you see here is a tree of development. This is our line of the Sapiens line. We've had some exchanges with Neanderthals, and we have some exchanges with this other group that was discovered more recently. It's suspected that actually all of these lineages had language. But what's crucial is that for most of our history as humankind, we have been in places that were rural, that had lower socioeconomic status, that had lower levels of formal education. I've never heard of Neanderthal school, ever. So I'm pretty sure that's like a new invention. And many other things that we take for granted, like the shape of this room, the number of people who are sitting, the fact of having this conversation between one person and 200 people. They're all coming from a blip in our history, right? So this is really interesting because when we're thinking about how biased our data sets are, we have no idea. Really, yes?
We know when language appeared?
Well, all the evidence suggests that Neanderthals had it. So we know it's at least as old as that. But it's hard to know. We can talk about it later. OK, so our estimates are super biased. We also suspect that when you think about how humans survive for most of their biological history, it's likely that right now we're moving towards a setting of homogenization. Everyone, if you go to Tokyo, if you go to St. Petersburg, if you go to Buenos Aires, actually, the cities look the same, the houses look the same, the food looks the same, the supermarkets look the same, and so on and so forth. But if you go across to other places, and if you think back in time, it's very likely that we are underestimating variation in these settings. So this is an example of a household in Papua New Guinea, where I was this summer, right before I got the email from Jean inviting me to speak here. You can see that this house, for instance, is up on stilts. So that's an interesting feature if you're a 1-year-old and you don't know how to walk. And this is an example from actually a culture that has now basically been lost from Eskimos and other related tribes in Greenland and other in northern Canada, etc. So you have to think that humans actually, before formal schooling, etc., we survived in all of these settings. And our vision, our audition, and perhaps other skills were also honed in these settings. Sorry, can you repeat that?
In 10,000 years, do humans evolve?
Excellent question. So the question here was, I forgot to repeat the previous one. The previous one was, do we know when language evolved? And the answer I gave, as you heard, is that we know for sure Neanderthals had it, so it must have been prior to that. The new question is, can we believe that there has been evolution in the last 10,000 years since we had agriculture? And the answer is there's probably for the most part no. Some of the everyday examples we can see of that is the fact that you see all these peoples from different places gathered here, and they grew up in different places. And we know that if you take someone from Africa and you put them in the States, they're the same, and so on and so forth. So we know that we're basically all very similar, and there's have been no changes. Particularly since actually the agricultural revolution didn't touch every site in the world at the same time. But sorry, I feel like I'm going off in this direction, but I wanted to make you aware of the fact that we actually have evolved in this very different setting and probably more diverse than we have now. OK, so we do have some examples of people who live in a way that's probably more similar to the way that we believe humans lived before the agricultural revolution, before the industrial revolution, and other revolutions like that. And these are called hunter-gatherer. That just means that their primary mode of survival is by getting animals and other resources from the environment. We know in terms of child rearing that there are some things that are universal across all groups of hunter-gatherers. In all of them, mothers and children are initially very close. They tend to sleep together. We know that once the child is above 1 year of age, actually they leave the mom and they sort of walk around with groups of other children, and they don't spend much time with adults. We also know that there's a lot of variation. So for instance, the fact that it's not the mother who takes care of the child will vary humongously across cultures. In some cultures, like for instance in the Papua New Guinea culture I visited, you can really see, you can go to one village and see a baby from another village that was brought here by 4 successive people who passed on the child. So you see a lot of allo care, other people caring for the child. Another things are different, how much the father is involved, to what extent the child is supposed to bring things and be self-provisioning. Okay. There's also quite a bit of variation in terms of how many children people have. And I can tell you a little bit more about this if you find it interesting. So to give you just 2 examples of groups I work with, in this one hunter-gatherer group that's based in Namibia, the average number of children per family is only 4. It's more than here, but it's certainly not very large. In fact, among the Chimane who live in Bolivia, the average number of children per family is 9. Some families have 15 children. That happens today. It's relatively common. One thing that is interesting about this is that we can eventually will be able to compare across hunter-gatherer cultures in terms of things like how much does the child speak, how much do people speak to the child, etc., etc. And we will know whether the fact that they have many more or many fewer brothers and sisters makes an impact in terms of how much time adults can spend with the key child, and in terms of how much peers, how much other older brothers and sisters can actually talk to them. But for now, I won't be talking about the Kum. I'll just be talking a little bit about the Chimane, just to give you an idea, and it's enough I want you to remember that I'm just going to talk about one case of hunter-gatherers, but I want you to bear in mind that this is not representing all hunter-gatherers everywhere, okay? Okay, so how do we study how hunter-gatherers learn their language, right? We want to de-bias our sample. The way to do this is to go there and study how this works. The way that we've been doing it is by using, primarily, by using a new technique called day-long recording. So these are recording devices, like the one I'm going to pull out of my code now. So we use often 2 kinds. This one's called the Lina, and it was developed in the States, and it's fantastic because it's very sturdy. It's a little bit heavy, and our kids in other places are very, very small. So some people don't like it so much. If you want to pass it around. And I really hope you give it back to me because it will be useless to you because it's all encrypted. You won't be able to use it, so don't take it away. Okay. The other one I won't pass around because, as you can see, it's just a USB key. It's nothing special, except that it was developed to spy on people, which we kind of do. It has a little switch at the top that allows you to record audio. And I love it because my fieldworker friends really like the fact that it only costs $15, whereas the Lina costs $300. And I repeat, it's useless to you. There is no market. Don't steal it and try to sell it. Yeah, and so if they break, you can replace it. If a child decides to jump into the river with it, it's OK. We can replace it, and so on and so forth. OK. Yeah, and so as you can see from the little photograph, we make special shirts, and the child can wear this for the whole day and go anywhere they would normally go, which is super great because then that means they can do whatever they were going to do anyway. OK. Now, that's great. It's very easy to accumulate a lot of data, but then we have a bit of a problem, which is, oh, that's a big audio file, and we need to find some data in it. And so let me tell you how we started going about this about 4 years ago. The first thing we did was sample. We took our audio, which starts in the morning and ends in the night. We skipped the first 30 minutes, and then we coded 1 minute every hour, by which I mean manually coded. You listen to it, and you decide, is the key child talking? Is some other child talking? Is it some adult talking? And so on and so forth. This only allowed us to label about 4 hours of data. That's not very much at all. Nonetheless, it's kind of interesting to know what do the results look like. And so in the graph you see here, each blob shows how much speech is directed to the child in minutes per hour, separating In white, how much is directly addressed to them. And in black is how much they overhear, okay? Most of our theories today are based on the idea that children only learn language from what is directly addressed to them. So it would only be this lower group of blobs that matters. On the x-axis is age, and each one of these represents one child, one of the 25 children that we studied that year. Okay, so by the way, in case you didn't notice, how much do children among the Chimane get talked to? It's about 1 minute per hour, okay, in our data. Now, 1 minute per hour, is that a lot or is that little? I'm not sure. Let's see what you think. What we'll do is we'll compare it to other data that looks at how much American children get talked to. So I would like you to vote whether you think that the results for the American kids, which I haven't mentioned yet, will show that they get talked to 0.5 minute per hour, so less than the Chimane kids. Raise your hand if you think that's true. Not many people think that's true. Let's see the next one. Raise your hand if you think that American kids are talked to more or less the same amount as the Chimane kids. A few people think that's true. How about 5 times more? Raise your hand if you think American kids are talked to 5 times more than the Chimane kids are talked to. Okay, quite a few people think that's true. And in fact, you're nearly right. They're actually talked to 10 times more. Okay? So that's a really big difference. One way to represent this is this one. If you imagine that they are awake about 12 hours a day, in an average day, a Chimane kid would have something like 12 minutes of speech per day. An American kid will basically have almost 2 hours. Some of you might think, well, that's quite a lot, but you're still not sure, but what does that mean? So I thought, okay, let's talk about something that you might be more interested in. Let's talk about an artificial agent that does something very simple, that transcribes speech. And so here I've assumed that, that humans can, figure out whatever someone is saying by the age of 10. Of course, I'm exaggerating. Humans can figure out what someone is saying a lot earlier than that. But I'm being nice, and I'm accumulating experience up to 10 years of age. This is how much experience child-directed speech Chimane person would have accumulated up to 10 years of age. This is how much an American person would have accumulated up to 10 years of age. And just to give you an idea, this is a supervised speech recognition system that was released a couple of years ago that has the same accuracy as the first PAISS transcription. And they need twice as much as the American kids have gotten. They need 20 times as much as the Chimane kids needed. And to make it even worse, those 350 million words that this systematic speech recognizer needed had to be done with supervision. Whereas, as was just mentioned, kids are actually learning all of this without basically supervision. Okay, so it seems that it's worthwhile looking at other cultures because this really gave us a new perspective into how much input you actually need to have a functioning language system. We've figured out that there's about 10-fold difference against the Americans. We went in and looked at who was talking to a child, and if you remove other children's speech who are talking to a child, then the difference is even bigger. So if it's true that adults are doing this thing where they're guessing the baby's frame of mind and adapting their speech to them, we know that other children are not very good at doing that. So that would mean that the difference between the Chimane kids and the American kids should be even bigger. But I know what you're thinking. You're saying, well, you're basing all of this in a tiny amount of data. And you might be really angry and you say, well, you're just telling me that their system is functional. How can we trust you? Maybe actually they are delayed compared to Americans. And some of you might be saying, yeah, we need to see some of these output measures about their development. And so this is something that I'm very keen in doing. And I think the way we need to do to move this from working on this tiny amount of data to using the hundreds and thousands of hours of data that we accumulated with this technique is to automatize this. So I'm going to talk to you a little bit about some of the steps we've taken to doing this. So the first task we try to solve is a very simple one, just deciding who talks when. So you take your acoustic signal and you say, well, in this bit, is it the child, is it the adult, or is it just background noise? It's not something that we care about. And so to figure this one out, what we did is organize a series of challenges. This year was the second one. It was presented at Interspeech 2 weeks ago. And so basically in challenges, are you guys familiar with challenges? Some of you are. Well, basically, you set up a data set, you set up some rules, and then anyone can try to win the challenge. And so to give you some idea of how people go about it, typically you have all of these steps. You extract some features, you cut it up into what could be turns or vocalizations. Then you extract some more features that are now at the level of the turns. You do some kind of clustering, and then you resegment once more, now with these new clusters that are likely something like talkers. Right now, the state-of-the-art systems are using, for this second step of feature extraction, are using embeddings from a DNN. And for the clustering, we're using PLDA, probabilistic linear discriminant analysis. So you can see that at least, so these X vectors are kind of newish. They're maybe 5 years old. PLDA is super old. Agglomeratic hierarchical clustering is also very old. The newest thing that we're doing, and I'm saying this with a small voice, is actually looking at architectures like this one, where you have a diarization system that might be like the one I just mentioned, and you have another system that what it's trying to do is figure out the domain. And the reason for this is that if you can imagine, if you were to wear a recording for a whole day, which I highly recommend because it's fun, you would do, sometimes you would be in a place like this that has a certain acoustic property, but then you go to lunch and it's a different place and it sounds different, and then you go to a supermarket and it sounds different, and then you go to a metro and that sounds different, and these are all different domains, right? And so if you have tried classifying images that are taken from a flow of images, the same thing happens with video. This can change a lot. So this is kind of the state of the art, and I'm saying it with a face like this because I really hope some of you will take on this challenge and try to do better. I think there's a lot to be gained in this field that, in a way, the techniques we're using are kind of tinkering on small parameters, but there's, we could be doing a lot better. OK, so that was the first one, the talker diarization. For that one, we have quite a bit of data that we can contribute for people who want to train. It's a hard task because you don't know whether there will be 0 or there will be 15 talkers in a little bit. The second one we tried is addressee classification, deciding whether someone is talking to the key child versus talking to someone else. And that one is only 2 classes. We did the challenge once, and no one beat the baseline. It was like the worst day of my life. You work and you prepare a data set and you say, this is going to work, we're going to have a wonderful classifier. It's only 2 classes, it should work, and it doesn't work. It was terrible. But I didn't lose hope. And the last one I tried is based on child vocalization types. And so to explain this one to you, I need to play you some clips, which might work or might not work. So basically, why this has to do with the output. Do we know that maybe are these kids maybe delayed compared to other kids? We know, as I told you before, that a lot of things happen before kids are 1 year of age. So we want to have measures that are sensitive to their development then. And so one of the things that happens is that their production actually becomes different. And that's nice because since we're doing audio recordings, we can actually get for free their productions. So let me see if I can play you some examples. Okay, so that's the simplest kind of vocalization. That's, I don't know if you noticed, but basically it's just, there's really not a lot of action up here in the mandible. It's like some vocal fold vibration, you know, going like, and that's about it. So that's the simplest kind, and we call that reflexive vocalizations. Reflexive means that it's a reflex. There's nothing you do about it. Now, the next example I'm going to give you is called non-canonical babbling. So this is more advanced, and it's purely, it's really linguistic. So you don't see this kind in other species, like in chimpanzees and so on. Okay, that was in addition to being pretty cute. Also not very well formed. Again, there's not much. I mean, the mouth is definitely moving, but it doesn't sound like when you say da da da. The father says da da da. That sounds very neat and very well done. Whereas for the baby, that's not the case at all. And once they're bigger, yeah. Once they're bigger, I think it's enough. You get the idea. It really sounds, their consonants sound really well defined, and they basically sound adult-like. Da 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 will sound like that. Okay. Okay. So in this next challenge that happened this year, we asked people to classify. We took clips from day-long recordings from kids from our Timane group, from American kids, and other groups. And we mixed them together to make sure that their identity was protected. And we had these different classes, as I mentioned: canonical, non-canonical. We had a junk class because we used an automatic speech recognition, speech parsing system, which also found some things that weren't actually the child, and we wanted to get rid of those. And we also had two non-speech categories, crying and laughing, so these are not linguistic in any way. What I'm showing you here is the baseline system that we put together for the challenge. So this was the system that the organizers put together. And we didn't think very hard because we had suffered from our previous experience of no one beating the baseline. So we said we're just going to do feature extraction and SVM. Very simple. People should be able to beat that. And I'm showing you here the confusion matrix across the different classes. You can see that our basic system does OK at finding canonical syllables. It does great at finding crying and OK at finding junk. But for finding laughing and non-canonical, it's doing very poorly. Laughing I'm less worried about because it's relatively infrequent. Babies apparently don't laugh very frequently for some reason. Okay. There was a winner. That was the good news. The bad news is that the winner was the winner only by 2 percentage points. They improved from 60% to 62%. So that wasn't amazing. And the other thing that was incredible was that they didn't improve by creating a system that was more complex. They didn't improve by using features that were more informed. They improved by using a pre-trained encoder-decoder system to generate more data. That's crazy to me, right? It's insane. So I really think that if you guys find this remotely interesting, you should come to talk to me, because you're going to beat this baseline, I'm sure, much better than these people. Okay, so I guess that's my challenge to you. Okay, so we are making steps to try to use these data better. But I really want to encourage you to think beyond the way that we think of classification today. It's very hard to build these data sets, and we will have a little bit of data, but as Jan often says, that will be like the little cherry up there, right? We need more people thinking about other ways to build robust classifiers to solve this. Now I'm going to change tack a little bit. First, I'm going to say, OK, I admit I haven't shown you a lot of data on the output, but you should believe me when I say that it seems that their language is completely functional and in a way equivalent to that of American kids. So our new model looks a bit like this. American kids get a lot of input, whereas Germanic kids get a little bit of input, and it's split between adults and other children. And yet it seems that in terms of output, they're producing at the same rate. They're developing at the same rate as Americans are. There are some open questions. Perhaps we will find that Germanic kids and like American kids can learn from other children's speech, and also from overheard speech. Now, I want to change tack because I want to talk about learnability properties, because one of the reasons why people were so obsessed with child-directed speech from adults is because the adult can solve many of the tasks. In a way, the adult is providing the supervision for this little agent. So what we want to know is to what extent can you learn from these less good, perhaps, instances of input. Speech, for instance, that's overheard rather than directed to you. We started looking at this for one specific domain, which is unsupervised word segmentation. I'm going to show you the results of a few experiments using this technique. In this technique, what's great is that we don't need to use real babies for the experiment. We can use computational models that would try to solve this task. And for this, we've developed a package that's available on GitHub. The pipeline looks like this. You just take some corpus. You remove the spaces between words. You segment it with some kind of algorithm. And this returns a segmented corpus that found where words begin and end. And you can evaluate that to make sure. So some example algorithms that we're using today. And the reason why I want to talk to you about this is because very often when we think of artificial intelligence, we think of things that are very complex. But now we want to know how babies do this. So we try to come up with strategies that are as simple as possible. The simplest strategies we have is something like you treat each sentence as a word, or you treat each syllable as a word. We have other strategies that we call sublexical, which try to find basically where you can cut, where words begin and end in a local way. You just look at things like transitional probabilities between syllables or between sounds, or some other ones. And the last kind of strategy is one that's informed, that assumes that actually when you have a corpus, this corpus contains a list of words, and your task is to find probably the optimal cutting of the corpus to regenerate that corpus with a very small dictionary. Okay. So basically, we have our learning functions that we manipulate because we implemented them, and we use as input transcribed speech corpora. They're transcribed because otherwise, from raw speech, this task is really, really hard. But if you want to know more about that, I'd be happy to tell you. Crucially, remember that we've removed the spaces between the words, and the task of the learner is tell us where words begin and end. So basically, put back the spaces. This allows us to look at things like something else that might change across when you go between, North America and any other place in the world. One of the things that will change is the actual language. So in particular, people have been looking at this word segmentation a lot in English, but it turns out that English is actually the worst language ever to study word segmentation, because every word basically is one syllable long. Most of them are, at least, particularly in child-directed speech. Compare this to a language like Inuktitut, where basically words are not one syllable long. They're a lot more complex. And Inuktitut is not a weird language, and I'm using that in the usual sense of weird. Most languages have more complexity than English. English is just unusually simple for some reason. Another thing that we've looked at is that bilingualism. We know that the majority of the world's population are bilinguals. We wanted to know whether this actually has a big impact on performance when you're trying to find beginnings and ends of words, where words begin and end. And so the way we do this is we just mix together transcripts to create a monolingual corpus by mixing together within a language, or you mix transcripts together across languages to create a bilingual corpus. And this way, everything is completely equalized across the monolingual and the bilingual conditions. Now, be ready, because I'm going to tell you the 3 factors of learnability then are: we implemented different processing algorithms, we looked at different languages, and we compared monolingual versus bilingual input. So we have one processing function variable and 2 input variables. Now, who thinks which of these 3 factors had the biggest impact on performance? Remember, the task is for the system to find where words begin and end. Who thinks that different processing algorithms were the biggest factor that explained differences in performance? That basically some algorithms were terrible and some algorithms were great and very easy and got really good performance. Who think that's true? 4 people. Okay. Who thinks that languages had a massive impact? Basically, some languages were really easy to segment and some languages were really hard to segment. A bunch of people. Excellent. Who thinks that having bilingual input was very confusing, and so systems that had bilingual input actually did much worse than systems that had monolingual input? Okay, few people. You know what's really interesting? The first group was right. But anyhow, let's step through this. The differences across algorithms are massive. What you see here on the y-axis is how well algorithms did. Though this is token F-score. And in this task, precision and recall are correlated. So it's not that we're using F-score and that we're hiding something. They're really correlated. On the x-axis here is the number of words that the system got, which is like the measure of how much input they got, okay? What you should see is that initially the algorithm's performance is kind of variable, but after that it's extremely stable, and the big difference is across different algorithms. So to point out a few of these, the ones in gray are the baseline ones, the really simple ones, cut in every syllable or consider every sentence to be a word. Those ones actually don't perform very well, except this one that does kind of okay, but this is only because the language I'm showing you is English. Much better are things like this green one you see, regardless of whether it got single sounds or syllables as input. It was doing above 60% correct. About 50% correct. And this green one is actually the one that was most informed, that was assuming that the corpus was actually generated from a dictionary and was trying to find the dictionary that best predicts that corpus. So basically a lexical approach to word segmentation. But one thing you can just retain is that actually there's a lot of variation that has to do with the learning function that the child, or in this case the system, brings to the task. Now, just to have an idea, this actually explains 40 to 60% in performance. In comparison, if you take Inuktitut versus English, on average, the difference will only be about 20%. It's very, very small. And if you look at monolingual versus bilingual, that basically has no impact. It's sometimes 0 in some of these conditions, particularly if the languages are a little bit different. So this is interesting because I'm very glad that you guys were so wrong. Because it shows how informative some of these experiments can be. And I think they can be informative, particularly for people in my field, because we have no direct access to the learning functions that babies have. But we can actually try to reverse engineer this particular case. So this is interesting, but I think it's just a first step. Finding beginnings and ends of words is just one of the many things that babies do. And so it would be really interesting for people who are interested in unsupervised language learning to think of other tasks in which we can compare children and artificial agents. Okay, so I'm just going to end on a slightly different note. I've been talking all this time about language because that's my key interest, but I think that some of these same ideas of thinking about how biased our views are, how biased our theoretical and empirical views are, can also be applied to other domains. And so I wanted to highlight one potential source of data for you that's called Databrary. It's a repository for all kinds of things related to development, particularly. But one of the things that they are best at is having videos of children's experience. So just to show you a few ones, I very much hope this will work. Yes, it does. Excellent. This is a child wearing a camera on their head. So this is the world seen from a 1-month-old who's being carried around by what I'm guessing is the mother or someone else who has long hair. And so this is kind of interesting because this is the child's visual system is actually being built using some of these images that I don't know how clear for some of you are. As children become older, the kinds of experience they will have will be a little bit different. And so let me show you, this is a 5-month-old. 5-month-olds can sit, most of them. And so the world kind of looks like this to them. Very cute, right? OK. And now, big time, baby walking. And now this is the world seen by a 1-year-old who's walking and, apparently sort of deciding they're going to crawl and then saying, oh, actually, walking was more fun. Let's go back to walking. OK. So I think these data sets are super interesting. Some of these videos are, the ones I'm showing are available, and they can be used by anyone. So if you want to go online and get them, you can. But in general, I wanted to highlight this idea that the kinds of environments that humans survive in are much more varied than these kinds of settings. So please remember this diversity between the Papua New Guinea and the Eskimo case when you're thinking of your own studies. And so I just wanted to end with a very brief summary. I started by talking about how all data sets, extant data sets on language acquisition are biased. I explained that this is particularly a problem because we're interested in the most intelligent natural agent we know, and this we have evolved in a substantially different setting. I talked about some naturalistic massive data sets that can be used in particular to confirm that some children get very little input and yet their culture develops a fully fledged language. I suggested one interesting path is to study learnability properties, which we can use because we can manipulate the input and the learning functions as we wish. And I highlighted some resources you can use, particularly if you're interested in vision. And I'm hoping that some of you will take on this challenge of thinking of classifiers that can make better use of the massive amounts of data that we cannot possibly annotate. And so I'll just end by thanking my team in Paris and my collaborators everywhere, and thanking you all for your attention.